Welcome to The Explainer, where we break down big, complex topics into something you can actually use, all in just a few minutes. Seriously, think about it. From the phone that's probably in your hand right now, to the electric cars quietly taking over our streets, batteries are everywhere. So today, we're going to crack one open, figuratively of course, and get right into the chemical magic that makes them work, and, maybe more importantly, why they all eventually die. All right. To get our heads around this, let's start with a really simple analogy. Forget the complicated chemistry for a second, and let's just think about a sandwich. So at its most basic level, a battery isn't some kind of magical box. It's really just a tiny, self-contained power plant. And the key idea here is that it converts energy. It doesn't create anything from scratch. It just unlocks the potential energy that's already packed inside its chemical ingredients, turning it into the electricity that powers our lives. Right, so the easiest way to picture a battery is as this special energy sandwich. You've got two very different slices of bread on the outside, and a really unique chemical filling that keeps them apart. And each one of these parts has a very, very specific job to do. Okay, so let's take a closer look inside that sandwich. Because how these pieces work together, well, it's kind of like an elegant dance of particles that creates the flow of electricity we call a current. First up, you have the anode. This is the negative side of the battery, one slice of our bread. And you can think of it as being absolutely packed with electrons that it is just dying to get rid of. It has this built-in chemical urge to push that energy out. And then on the other side, you've got the cathode, the positive terminal. This is our other slice of bread. And chemically speaking, it is hungry. It desperately wants the exact same electrons that the anode is trying to give away. And that tension, that difference in potential between the two sides, is what drives this whole entire process. Now for the filling in the middle, the electrolyte. This stuff is the brilliant gatekeeper of the whole operation. It's soaked with charged particles called ions, and it lets them pass through, no problem. But, and this is crucial, it blocks the electrons, forcing them to find another way to get to the other side. And here is where the magic happens. The second you connect your phone, you create that other way. You give the electrons an external path to travel. So they rush out of the anode, flow through the circuits of your device, powering it up, and race over to the waiting cathode. But for all of that to work, the charge has to stay balanced. So at the very same time, ions are shuttling through the electrolyte in the middle. It's this perfect partnership. One flow can't happen without the other. Okay, so if it's just this elegant chemical reaction, this flow of particles from one side to the other, why do all rechargeable batteries eventually fade and die? I mean, why can't they just do this forever? Well, it turns out the answer is a pretty wild paradox. The very thing that forms inside a modern battery to keep it safe and stable is also the thing that slowly but surely kills it. I want you to meet this solid electrolyte interface, or what everyone just calls the SEI layer. Think of it like this. It's a super thin film that forms on the anode the very first time you charge up a new battery. Its job is absolutely critical. It's a shield that stops the electrolyte from just getting completely used up in one go. But here's the thing. This isn't some perfect, clean shield. It's actually a messy, complex mosaic of different chemical byproducts. But it's cleverly messy. It's built in a way that lets the important lithium ions wiggle through while blocking all the other unwanted side reactions. It's what makes the battery stable enough to actually use. But here's the tragedy of the SEI layer. While it forms to protect the battery, with every single charge and discharge cycle, it grows just a little bit thicker. It gets stressed, it cracks, it has to reform, and every time it does that, it uses up a little bit of the lithium and a little bit of the electrolyte, the very things the battery needs to hold a charge. This is capacity fade. This is why your 2-year-old phone doesn't last all day anymore. And check this out. This is what that decay actually looks like up close. A nice smooth surface gets all cracked and cluttered and just junky after hundreds of cycles. And it gets even worse when things get hot. It literally becomes harder for the ions to push through all that gunk, choking the battery's performance over time. Now, of course, this whole process happens a little differently depending on the battery's chemistry. Because not all batteries are built the same. There's a whole family of them, really, each designed for a different job, and each with its own unique set of strengths and weaknesses. The biggest split in the family is between primary and secondary batteries. Primary batteries are the disposable ones, single use. The chemical reaction inside is a one-way street. Once it's done, it's done. Secondary batteries are the rechargeable ones. You can apply an electrical current to reverse the reaction, basically pushing everything back to where it started, ready to go again. So let's look at 3 of the big players. You've got your standard alkaline batteries, the disposables in your TV remote. Cheap, reliable, you just toss them when they're dead. Then there's lead acid. These are the heavy brutes that have been starting our cars for 100 years. They're powerful, but they're not great at storing a lot of energy for their weight. And then you have the superstar, lithium-ion. It absolutely dominates our world of phones, laptops, and EVs because it can pack an incredible amount of energy into a really lightweight package. So, knowing what we know now about how they work and how they fail, what's next? Where is all this battery tech actually going? Look at that number, 2,600 gigawatt hours. That is the projected global demand for batteries by 2030. It's a staggering increase, and it's being driven by 2 massive shifts: the move to electric vehicles and the desperate need for huge batteries to store power from solar and wind farms. So, how in the world are we going to meet that kind of demand? Well, the game is changing. For decades, it was basically just mixing chemicals in a lab and hoping for the best. Now, scientists are using supercomputers to design brand new materials from the atom up, predicting how they'll work before they even make them. It's a total revolution. The perfect battery. It's still out there, but the race is on to find it. From solid-state designs that are safer and could charge in just minutes to new chemistries that use cheaper, more common materials, the next big breakthrough is coming. And when it does, it could fundamentally change our world. Thanks for joining this explainer.